Good evening, everyone. This is Dr. Wang from my home. This is the first time I shoot a video for my class. This is no format I don't like. You guys know that because I miss you guys. I want to see you guys. However, at this special moment, I think this is the best way we continue our education. So today we are going to discuss the reactions of benzene ring. So chapter 16. Because some of you missed the first discussion last Thursday, I will first go very quickly about the reactions we learned in the previous discussion. Basically, the key reaction we learned last Thursday is the electrophilic aromatic substitution reaction. So the key point for this electrophilic aromatic substitution reaction is how we generate this electrophile. The electrophile basically is something or a molecule that bears a positive charge. We know there are 6 electrons in this benzene ring. Of course, the electrophilic, something bears positive charge, will react with the electrons to form a new bond. So the result of this reaction basically is one of the hydrogen in the benzene ring is replaced by this electrophile. So first example for this electrophilic substitution reaction is halogenation reaction, either chlorination or bromination reaction. So I want to remind you the catalyst here, iron chloride or iron bromide, which is very critical for this electrophilic substitution reaction. This is a mechanism here. Again, the key point for this type of reaction is how we generated something which bear positive charge. Here in this structure, you see this bromine atom bears positive charge, which can do the electrophilic substitution reaction. The second electrophilic substitution reaction is nitration reaction. Basically, a benzene ring is nitrated by nitric acid plus some sulfuric acid. So the result is one of the hydrogen in the benzene ring is replaced by the nitro group. So the third example for electrophilic substitution reaction is a sulfonation reaction with the sulfur trioxide plus the sulfuric acid. The result is one of the hydrogen in the benzene ring is replaced by the sulfonic acid groups. So this reaction is pretty simple reaction, very common organic reaction. That's also a reaction I did for almost 10 years before I joined PPG. Mechanism, I hope you can read the mechanism by yourself. Again, whenever you have a question, please don't hesitate to ask. So another example is Alfredo-Kraft alkylation reaction. This is a very, very important reaction, much more important than the reaction I did for 10 years. So basically, it's alkyl group replaced. The alkyl group replaced one of the hydrogen on the benzene ring with the aluminum chloride as the catalyst. So this is one example here. So mechanism of the Friedel-Crafts alkylation reaction. Again, the key point is how we generate something bears a positive charge. You see, this is the electrophile. Something bear positive charge. So the mechanism, the electrophile reacts with the electrons from the benzene ring to form the substituted product. Well, because for the Friedel-Crafts reaction, the intermediate is the carbon cation. We learned in I believe chapter 9, carbon cation can do rearrangement reaction. So this is the carbon cation's rearrangement. We can form a secondary carbon cation. If we do the 1,2 hydride shift, we can form the tertiary carbon cation. Of course, tertiary carbon cation is more stable than secondary carbon cation. So eventually, the tertiary carbon cation is the real electrophile to do the electrophilic substitution reaction. So the final product you see here, particularly the alkyl side, the structure of alkyl is different from the starting materials because of this carbon cations rearrangement reaction. So more carbon cations rearrangement reaction. The second type of Friedel-Crafts reaction is acylation reaction. Basically, benzene ring react with the acid chloride. We use the same catalyst, aluminum chloride. We formed ketone molecules. So here's the mechanism. Again, the key point is how we generate something which bear some positive charge. The positive charge will react with the electrons in the benzene ring. This is called a Friedel-Crafts acylation reaction. So one more example for Friedel-Crafts acylation reaction. Basically, this is an intramolecular reaction. Intramolecular reaction, which means the molecules react with itself. You see, the left side of this molecule is the benzene ring. The right side is acid chloride, and we have a proper catalyst, aluminum chloride. So one of the hydrogen, I don't want to see any hydrogen work, but in this case, only this hydrogen. This hydrogen is substituted by this acid chloride group. So chloride serves as leaving group. We form a new sigma bond here because the product basically here is a 6 membrane. I told you before, 6 is a magic number. That's the reaction only occurs in this position, not this position, not this position, because if this position or this position would not give us the 6, the magic 6 number here. Okay, that's all we learned in the previous discussion, and here today we are going to continue the reactions of electrophilic substitution reaction. And we know electrophile will attack the electrons in the benzene ring to do the electrophilic substitution reaction. So the electrons density in the benzene ring is very critical. We want to analyze the electrons density in the benzene ring. It is higher than benzene or lower than benzene. So when we do this work analyzing the electron density, we needed to know the effect of the substituted groups. Like in this case, it's a amine group AN2. In this case is the methyl group. They are electron withdrawing or they are donating groups. So basically we have two effects to analyze. The first one is inductive effect. Inductive effect, basically we just need to know the electronegativity. Pretty simple. So we know we have a table of electronegativity of different atoms, like in this case, this bond, nitrogen connected to carbon here. Nitrogen, of course, is higher electronegative atom than carbon here. So the electron, these two electrons, is more towards the nitrogen group. So this nitrogen here is an electron withdrawing group because, again, electron pull the electrons towards itself. So in a second case, this benzene is attached to a carbon group, carbon and a carbon. This is a carbon, this is a carbon. But we know because this carbon attached to 3 hydrogens. So this carbon bears slightly more electrons than this carbon. So we see this carbon can donate electrons, push the electrons to the benzene ring. Again, because this carbon attached to 3 hydrogen, but there is no hydrogen here. So this carbon donate electrons towards the benzene ring. So in this case, we call this the electron donating inductive effect. Again, inductive effect basically is the electronegativity. Either pull the electron away or push the electron towards the benzene ring. The second effect we want to know is the resonance effect. The good news for you guys is that we have only 2 effects. Either electronegative, that's inductive effect, or the resonance effect. This is the second effect. So in this case, like this benzene ring is attached to the aldehyde groups here. If we draw the resonance structure, again, resonance effect, basically we just draw the resonance structure. So oxygen, a very strong electron withdrawing atom, basically we draw the resonance structures. Resonance structures. So this is all the resonance structures we possibly have. So if we take a look at the resonance structure here, you see a positive charge here, positive charge. So which means that the aldehyde can pull the electron away from the benzene ring. So the benzene ring actually at some point, not each point, but this point, this 3 points, they bears the positive charge. So the overall effect, the overall electron density in this benzene ring is decreased. So we call this aldehyde is an electron withdrawing group via the resonance effect. So another groups, amine groups, NH2 here, you see, if we draw the resonance structure of an amine attached with the benzene ring, we can have different types of resonance structures. And if we check the details of the resonance structure, we can see here, you see in this carbon, there is a pure negative charge, a pure negative charge, a pure negative. Basically, the amine, this pair of 9 shared of electrons basically give its electron density towards the benzene ring. So we consider this amine group is an electron donating group. Basically, why there we have a negative charge here because of these pairs of electrons. So we consider this amine again is electron donating group where the resonance effect. So again, we have 2 effects. The inductive effect basically is the electronegativity. The second effect is the resonance effect. Basically, we need to draw the resonance structure and analyze the resonance structures will reinforce, increase the electron density in the benzene ring, or pull the electron away, which decrease the electron density in this benzene ring. All right, so again, we have 2 effects, inductive effect and the resonance effect. Let's take a look at an example here. The nitro group, NO2. The nitro group, nitrobenzene. This is the structure, the lowest structure of a nitrobenzene. So if we draw a valid lowest structure, we can see this nitrogen atom here basically has a positive charge and this oxygen has a negative charge. Is it an electron withdrawing group or it is an electron donating group? So again, we need to analyze 2 effects. The first one is inductive effect. The second one is a resonance effect. So again, nitrogen attached to carbon. Inductive effect, basically the electronegativity. So nitrogen is a stronger electronegative atom than carbon here. So the inductive effect is the nitrogen will pull the electron from the benzene towards itself. So it is a electron withdrawing group because pull the electron towards itself. The second effect is called the resonance effect. So when we draw the resonance structure, let's draw the resonance structure. You know, this is first resonance structure, this is second resonance structure, third, fourth resonance structure. We see if we check this resonance structure, you see there is a positive charge here. If we check the second positive or third resonance structure, they all have a carbon which bears positive charge, which means the resonance, you see, the resonance structures pull the electron away from the benzene ring. So the resonance effect pull the electron away. So the resonance effect makes the benzene ring has less electron density. So benzene ring is an electron withdrawing group. Again, inductive effect means it pulls electron away. The resonance effect also pulls the electrons away from the electron. So we can see electron group is electron with a totally electron withdrawing group. Well, we have definitions for different positions. You know, this is the nitrobenzene, the NO2 groups is here. So the two carbons here, which is connected to this carbon, you see these two positions, we call them ortho position. Another two carbons at this position, we call them a meta position. And this carbon, we call it a para position. You know why we call this? You know, that's probably from some languages. I don't know. You know, it's just a definition. We need definitely to remember ortho, meta, and the para positions. Well, let's take a look of this again. The structures of the resonance structures. 1, 2, 3. You see, it's not every carbon in this benzene ring bear positive charge. Only 3 of them bear positive charge. We know electrophilic substitution reaction is an electrophile, something bear a positive charge, react with the electrons with the benzene ring. So if this nitro group reduce the electron density in this benzene ring, so the electrophilic substitution reaction will be decreased. Again, because the electron density here is reduced compared to benzene ring. So we can see nitro group is a deactivator because again, the electron density here is reduced by this nitro group. So the reactivity also reduced. So we call it is a deactivator. And one more consequence from this nitro group, again, if we have an electrophile, something bear a positive charge here, something bear a positive charge here, let's say it's in your mind, so it will attack it's going to replace one of the hydrogen here. So it's going to replace this one, or it's going, let's say this structure, it's going to replace this one or replace this one. So again, electrophile basically bear positive charge. So if I bear a positive charge here, I want to attack this benzene ring, I want to attack this position, not this position. The reason is because this position bear a positive charge. Not only this position, but this position and this position. So two positions does not bear positive charge. Actually, this one and this one. See, this one and this one. Basically, two matter position. That's why we have a definition of a matter position, because all the ortho position and the para position, ortho position, para position, they all carry some positive charge. If you have an electrophile which bears positive charge, now I want to avoid it to attack you, but this two, the matter position, because you don't have extra positive charge. That's why we see nitro group is the matter director. So if we have an electrophilic substitution reaction, it's going to occur either here or here, but not here, not here, not here. All right, let's take a look at the real reaction. We have a nitrobenzene here. We want to introduce the second nitro group. Again, the nitration react. This is a nitration reaction. We use a nitric acid plus a sulfuric acid. So, if we check the product, we have a mixture. It could be the new nitro group, could be here, could be here, could be here. And we found 93, the majority is at this position. So this is nitro, this is original nitro. Again, this is meta, this is meta, this is para, this is, this is ortho. This is two ortho position, this is para position, this is meta position. So, nitro group, we analyzed in the previous slide, nitro groups is meta director. So see, meta is the major product in this reaction, and that this reaction would be slower than the nitration reaction of benzene without this nitro group again, because this nitro group is a very strong electron withdrawing group. Let's take a look at another group, the methyl group. Methyl group, the carbon, because this carbon attached to three hydrogen, so this carbon bears some negative charge. So it's a negative charge. It's going to push this two electron towards the benzene ring, or it's an electron donating. Push the electron, donate the electron to the benzene ring. So we can say this methyl group is activator, which means the electron density in this benzene ring is higher than pure benzene without the methyl group. So this reaction is faster than the bromination of pure benzene. And if we check the substitution reaction product, we can find 40% product on the ortho position, 60% on the para position. This is para position only. Trace, pretty much less than 1%. It's the matter product. So again, this is the activators effect. Activators, if you have activators, your electrophilic substitution reactions product is either ortho product or para product, but not matter product. This is compare. Let's compare. You see, this is a matter director. So the activator electron withdrawing group will give us matter as the major product. The electron donating group will give us ortho and the para substituted product. Again, basically when we do the substitution reaction, we have 1, 2, 3, 4, 5 hydrogen. But when they do the reaction, they do not react equally. They prefer for electron donating group here, they preferred from either ortho product or para product. Now let's analyze the amine group. This is very common for many organic synthesis. The amine group is amine electron donating or electron withdrawing group. Alright, okay, I already give you the answer here. But amine basically is the electron donating group here. But I want you to know why amine is the electron donating group here. I remember when I was at your age, I was really confused by this chapter by groups like amine group and nitro group. Are they electron donating or electron withdrawing? So, but I don't want you to be confused. I want to make this very clear. So, if you want to know a group, either amine or something else, are they electron donating or they are electron withdrawing group? You only need to analyze two effects. Again, two effects. Inductive effect or resonance effect. Then you can draw your conclusion. Most of the cases you can draw a conclusion. It is electron donating or electron withdrawing group. Let's take a look at the inductive effect. When we see the inductive effect, basically we just only analyze this bond, nitrogen and the carbon bond here. Because nitrogen is a stronger electronegative atom, it's going to pull the electron away from this bond or from the benzene ring. So we see nitrogen or amine group here is the electron withdrawing group. Pull the electrons away. So it is a deactivator. Pull the electrons away. Okay, this is only one effect. The second effect is basically the resonance effect. Resonance effect, basically we need to draw the resonance structures of this aminobenzene. So there is a pair of non-shared electrons. We can draw the resonance, move the pi bond or the lone pair electrons around. We form this resonance structure. We continue move the pi bond and lone pair electrons around. We can form the second and third and the fourth resonance structures. And if we take a look at the details of this resonance structure, you see one carbon in this benzene ring bears negative charge. Second carbon bears a negative charge. This is a ortho position. This is a para position. Again, relative to amine group. This is just the border carbon, a neighboring carbon. This is the ortho position. This is a para position. This is another ortho position. So we can say either both ortho position and a para position. Third position, two ortho and para position actually bear a negative charge. So in other words, amine group, the nitrogen, the two electrons on this electron, the two electrons on this nitrogen group basically donating or giving the two electrons to the benzene ring, which reinforce or increase the electron density of this benzene ring. Or in other words, we can say amine group is an electron donating group with the three different resonance structures. Now here's the problem, here's the point. I'm so confused. Sometimes I heard my professor said, oh, nitrogen is electron withdrawing, pull the electron away. Oh, amine group is electron donating group, giving group. Well, is it the overall effect? Is it electron donating or electron withdrawing? So if you read the textbooks, pretty much all the textbooks just give you the conclusion, oh, electron is an electron donating group, like the title I have for this slide. I don't think that's clear. So we have to do many experiments, and finally the organic chemist figure out this resonance effect is a much more player than the resonance effect. So it's much more important than the inductive effect, which means that the giving effect is much stronger than the pulling effect. So we can see amine basically is a very strong electron donating group. It is a very strong ortho para director, although the inductive effect of this nitrogen group is the slightly the effect, the slightly pull the electrons away from the benzene ring. So remember, amine has two contradicted effects, but the overall effect is amine is a very strong electron donating group. And amine is also a very strong ortho para director in electrophilic substitution reactions. Alright, halogens. I don't think you can find those pictures from our textbook. Basically, I draw this resonance structure because halogen is very special. So is halogen is a donate or withdraw? A donate or withdraw electron from the benzene. So again, we need to analyze the two effects, inductive effect first. So chloride here is a stronger electronegative atom than carbon, of course. So this chloride, the inductive effect is pulling electron away from the benzene ring towards chlorine. However, we still have a second effect too. Inductive resonance effect. Resonance effect basically means we need to draw the resonance structures. We have 3 pairs of non-shared electron in this chlorine atom. We can draw different resonance structures. You see in this resonance structure a negative charge here at the ortho position, negative charge onto the para position, negative charge onto the ortho position. Well, two effects work against each other. Inductive effect pull the electron away. Resonance effect giving electrons towards the benzene ring. They work against each other. So is it an electron donating or electron withdrawing group? So I have to say again, we have to do a lot of experiment to check, is this chlorine here, the overall effect is giving electron or withdrawing effect. So this is tough, but I think it's not a very big deal because this type of reaction actually is not super important for organic synthesis. The resonance effect is almost to inductive effect. And halogen, in this case, is also para director. So they are equal, and this just observations. It's hard to use the the donating or withdrawing theory to explain here. So here probably just need to have to remember halogen is also para director. So the reaction will occurs here ortho and para position, but the electron donating resonance effect and the electron withdrawing inductive effect, they are mostly equal. Here, this is a table. This is a very important table. Well, we analyzed amine, so hydroxyl group, or ether group, or amide group, or alkyl group, or like methyl group. They are activating groups because they give electrons towards the benzene ring, so they increase the reactivity. And they are also the ortho para directors. So like aldehyde, like ketones or esters, acid, nitrile, sulfonic acid, nitro group, quaternary ammonium cation here. This nitrogen bears pure positive charge. Of course, it's going to strongly give the electrons towards the benzene ring because I have positive charge. So these are all deactivating groups. And the product is matter director. We already analyzed this example. The nitrobenzene always prefer to give a matter product. So the only special case exceptions is the halogen. If we have a halogen atom on benzene ring, it's considered a deactivating group. But it gives the ortho para director. So that's the only exception. Normally, activating groups give you ortho or para substituted product. So the electron withdrawing group, they are a deactivating group. Deactivators give you matter, the substituted product. But halogen, benzene chloride, or benzene bromide, they are ortho para director, give you ortho para substituted product. But they considered a deactivating groups. Again, this is the only special case. All right, let's take a look. More examples of electron substitutions reactions. Benzene, this is phenol. Benzene attached with the OH group here. If we do a bromination reaction with the iron bromide catalyst, this OH group. OH groups are very strong electron donating groups, donating the electron towards this benzene ring. So the electron density here is much higher than benzene. So we are able to get a tri-substituted, three hydrogens replaced by bromine. Again, strong donating group increase the reactivity, give us ortho para substituted product. See here, ortho para substituted product. So without catalyst, there is the only one, because without catalyst, the reactivity of this bromination reaction decreased. So only one hydrogen on the benzene ring is substituted by bromine. So it is either ortho or para position. There is no substitution at the meta position. You said these two met relatively to this hydroxyl group. That's how you analyze the reaction product of electrophilic substitution reaction. And here I want to show you some limitations of a Friedel-Crafts reaction. So we discussed the Friedel-Crafts reaction in the first chapter. So basically a benzene ring without this nitro group react with the alkyl halide to the Friedel-Crafts alkylation reaction. Aluminum chloride is the catalyst. So basically, if we have a nitro group in the benzene ring, there is no Friedel-Crafts at all. Why? It's because this nitro group is a very strong deactivator, or in other words, this is a very strong electron withdrawing group. So we have, it is true, we have 6 electrons in this benzene ring, but whenever we have a very strong electron withdrawing group, it will pull the 6 electrons towards the nitrogen or nitro groups here. So which means that the electron density in this benzene ring significantly reduced. Although we have something electrophile, again, electrophilic substitution reactions, the K is how we generate electrophile. We have an electrophile here, something bears positive charge, but because of the electron density in this benzene ring significantly reduced by this nitro group, there is no reaction between the electrophile and this benzene ring. And another limitation reaction with this aminobenzene. We know aminobenzene, this is a activator. So it's a strong electron donating group. So basically increase the electron density of this benzene ring. So the reactivity should be much higher than benzene. However, we cannot use this aminobenzene to do the Friedel-Crafts reaction because the catalyst again for the Friedel-Crafts reaction, aluminum chloride. Aluminum chloride is a very strong acid, okay, basically, because there are only 6 electrons around this aluminum atom. So it's acid. So it wants to form octet structure. So it happens a nitrogen group here. I have 2 electrons. I can share with you to do an acid-base reaction. See, this is base, provided 2 electrons. This is acid, acceptor of 2 electrons. Before they can do with the alkyl halide, before this benzene ring react with this alkyl halide group to do the Friedel-Crafts reaction, the catalyst first react with the amine to do the acid-base reaction. So whenever the acid-base reaction occurs at this complex form, that's basically ended the Friedel-Crafts reaction, or we can say there is no Friedel-Crafts reaction at all. 2 limitations: very strong electron withdrawing group, or amine groups here. If amine groups can do an acid-base reaction, we do not have a Friedel-Crafts reaction. And more about a Friedel-Crafts reaction. If we can do a Friedel-Crafts reaction with benzene, alkylation reaction, we can replace one of the protein here by alkyl group. If at this moment, if we still have an alkyl group here, so this reaction will occur immediately to form a di-substituted product. Actually, 2 hydrogen replaced by the alkyl group in this reaction. It's hard to, if we have enough alkyl halide here, it's hard to stop here. The reason is we can do the first step reaction. Whenever the alkyl group introduced to the benzene ring, this is an electron donator, donating its electron towards the benzene ring. So the electron density here is higher than here. So if we have a more alkyl halide, this reaction, the second step reaction, actually faster than first reaction, again because the electron density in this benzene ring is higher than this benzene ring. So when we do the second step reaction, again, this is an electron donator. It's an ortho para director. So the second step, we have 1, 2, 3, 4, 5 hydrogen to replace, but they do not react equally. It's only the ortho position or para position. Excuse me. Will do this substitution reaction because this is a electron donating group and it is the ortho para director. So again, so if we have amine group, there is no Freddy or Kraft reaction. This is the same with this one. Okay, let's take a look of a more substituted benzene here. So like in this benzene ring, we have two substituents, methyl group and the nitro group. If we do the bromination reaction, it's the electrophilic substitution reaction, where the substitution reaction will occur. We have 1, 2, 3, 4, 4 carbons, 4 hydrogens can be replaced. So where it will be, or they will be equally occur. Well, let's take a look at the structure. The methyl group we know is electron donating group. So it is an ortho para director. So we will prefer here and here, but not here because this position already occupied. And let's analyze the second group. It's the nitro group. Nitro group is a very strong electron withdrawing group. So withdrawing group is the matter director. Matter director prefers the bromination and the meta position. You see, this is a nitro group. This is a meta group relative to nitro group. This is also an ortho group relative to methyl group. So both effect, either from methyl group or from the nitro group, prefer the reaction to occur at this position. So if we do the experiment, we can confirm. So this will be the final product. So this is a good example because we have a team. Both the team has two players. They worked as a good team. They worked together to form a good product. The second example here. So we have two groups here. So we have amine groups here. We have a methyl group here. So amine is a strong. I would say this is a stronger electron donating group than methyl group. Both groups are electron donating group. So the methyl group prefer this bromination reaction here at ortho position, but this amide group prefer to have the reaction here at this two position. So if we have only one hydrogen would be replaced by the bromine, it's going to be either here or here. The reason is, we are a team, but we have different opinion. I'm the chairperson. I don't want to say this. That's a very bad example. I'm the stronger ortho para director. I'm stronger than you, methyl group. If we go back to the table, see, amide group is stronger than methyl group, alkyl group. So that's why this table is very important table. I hope you can remember this group, not only this group but also like the order. This is also the order of this is strongest one. This is also strongest one. So back to this reaction, I'm a stronger ortho para direct, so I prefer the bromination reaction either here or here. So sorry, you are not strong enough. And the third effect is a steric effect. This is very easy to understand. You have a methyl group here. There is another methyl group here. We are brothers. We have the same electron donating group right here. So I prefer either here or here. This brother prefer either here and here. Basically, you know, they are good team members, they are good brothers. All right, to make us all happy, let's have the reaction. No. Uh, if 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 we want them happy, they prefer to occur here to do the bromination here at this position. But unfortunately, whenever you know the space, if we consider the space, this is the least space. Least space. The two brothers already occupied, you know, this area. So if we do the reaction, actually the bromination either here or here, this the second preferred position due to this steric effect. Well, let's do some practice with the knowledge we learned today. I want to make a benzene with a bromine and a nitro group in this benzene. Bromine in this position, nitro group this position. Of course, we need to make this compound from benzene molecule. That's good. We need to introduce a bromine and a nitro group in benzene. So the question is, which one should I introduce first? Should I introduce this first, or should I introduce this first? Let's take a look. If we introduce this bromine group first, if we forget about this nitro, this would be the second step. If we do this first, we introduce bromine group, so and we with the table we can check bromine is actually ortho para position. This is ortho, this is ortho, this is para. Then we do the nitration reaction. We possibly can have the nitro groups at this position. First bromine, second nitro group here again because this is a para ortho para director. This is possible. And second option is, oh, okay, forget about the bromine. Let's introduce the nitro group first. Nitro group is introduced at this position. Nitro is a very strong electron withdrawing group, and we know nitro group is a very strong meta director. So whenever we want to introduce the second bromine group, so because this is meta director, this would be the meta position relative to nitro group. So the nitro group actually will be introduced here, not at this position. So by analyzing this structure, if we really want to make this group, now we have to do the option 1. Introduce this group first, then introduce this group first. If we introduce this group first, we will never able to get the nitro group at this position. Alright, so this is the synthesis of this nitro bromine benzene. Again, this is the benzene. We can do the bromination reaction. Just introduce one bromine group here, then do the nitration reaction of this brominated benzene. So because this bromine group is ortho, this is ortho meta director, so we are either going to have this product or this product. It's probably a mixture, but at least we can make this molecule, target molecule. This is the first step, bromine, second step, nitro group. If we reverse the order, reintroduce the nitro group first. To do the nitration reaction, introduce the nitro group first. Then do the bromination reaction. This is the bromination reaction. And because of the nitro group is a meta director, so the reaction will be at the meta position. This is the meta position, or this is also a meta position. So the bromine group either here or here. You see, two molecules. This is the target molecule. This is similar but totally different molecules. All right, that's all I want to share as the second discussion for this aromatic substitution reactions. In this discussion, we analyzed the the two effect, inductive effect or resonance effect. By analyzing the two effects, we can have a conclusion. Substituent group on benzene ring. It is an electron withdrawing group, or electron withdrawing or electron donating group. Electron donating group will increase the electron density of the benzene ring. It is an activator. And normally activator will give us ortho or para-substituted product. So electron withdrawing group like a nitro group, they are considered a deactivator because they decreased the electron density in the benzene ring. And if we introduce the second group, they normally give us a meta-substituted product, meta relative to this nitro group, because this is a strong electron donating group. The halogens substituted on the benzene is the special case, and you need to remember they are a deactivator or an activator. It's also a para deactivator. All right, that's for the second discussion. Talk to you later. Bye.